Hi, thanks for watching this. This is going to be another example of Doppler shift applied to some real-life situation. Of course, we're going to make some simplifying assumptions and so on, but it's a place in physics where the Doppler shift tends to be highly relevant, namely in astronomy. So we're going to analyze a binary star system. What does it mean? I've got two stars, not just one, and they're circling around each other under their own gravitational pull, right? So this one attracts this one attracts this one. They're fairly common out there in space. So, this is an example that you might well come across if you go into astrophysics. Or you just care about it. So we're going to make the huge assumption that those two stars have the same mass. Right? That would be a giant coincidence, but there are systems where they're fairly close in mass to each other. There's some where they're hugely different, right? So the types of star systems out there, there are many and varied. And more often than not, those systems are so far away from us that we can't actually see two stars, right? They're too close together from looking at them, even with the best telescopes. They together appear as a single bright spot in the sky. So we can't, say, measure that radius of that circle that they're both making. But here's my claim. Just by looking at the light of those stars, the light, that single sort of dot that we see, right, I'm going to be able to figure out what is the distance between the stars. In other words, what is this radius of that circle, and not only that, and also infer what the mass of the stars actually is. Right, that is crazy, right? I'm just looking at the light emitted by this dot in the sky. Of course, I'm making the assumption of the same mass, but even if I didn't, it would make it a bit more complicated. In the end, the principle is the same, right? We're trying to follow the reasoning here, and it's based on Doppler shift observation. So how can I do it? How can I find the distance just based on observing the light emitted by the stars? So there's one key of insight that we're going to need that I wrote down here for you, right? So stars don't just emit light. They don't just emit a sort of light at some arbitrary color, right? They emit light, and that light is going to have spectral lines. Now, if you've done chemistry, you probably know what those are. They're essentially lines in the spectrum of light. So all those different frequencies get emitted, but there are certain lines that appear in that pattern. And those lines are a result of the particular elements that the star is made of. Also, if things are not stars, we do spectroscopy. And they come ultimately from transitions between the atomic levels, down on the microscopic scales. Quantum physics. We're not going to worry about it, we just care that they exist. So we expect to see certain lines, we can look for them. We can look for those patterns, we can analyze essentially what the star is made of, and let's say we're observing our star and we know there should be a wavelength emitted that is 656 nanometers long, right? So the 656 nanometer hydrogen line, that's in the visible spectrum. We're able to see that. So again, why 656 nanometers? Quantum mechanics, makes the prediction that at this wavelength, there's going to be a lot of light emitted, based on what we know about atomic structure, energy levels, and so on. Right? We just care, okay, this is the line. This is a wavelength where we expect to see an emission. That's the one key we need. So 656 nanometers, what's the frequency? Well, I take the speed of light, that's 300 million meters per second, divided by the wavelength, turned into meters, it gives me a frequency 4.5732 times 10 to the 14 hertz. Alright, of course not exactly that, it has a few more digits, but we're going to round to that. Assume this is the exact frequency. So that's what we expect. And now we observe the star and we look for that line. Now here's what we actually see. This is the data. Here in the middle, is 4.5732, excuse me, times 10 to the 14 hertz. Right. But what we observe is actually that that line seems to shift back and forth. Really, what we would be observing is two of those lines moving opposite. But just focus on one. One of them, it shifts like that. So sometimes a little bit higher, the frequency is a little bit higher, sometimes the frequency is a little bit lower. It sort of seems to be going back and forth. What explains that? Well, let's look at our star system. Right. Here's our star system. The star's going this way. The star right now is going this way. So, at one point, this star is migrating away from us. So that means we are down here somewhere far away, right? The light gets Doppler shifted with the source receding. Here the light gets Doppler shifted with the source approaching us, and of course all the areas in between where it's essentially going sideways. Right, so you imagine myself to be somewhere far away in this direction. This is getting away from us, this is getting closer to us. It doesn't matter how far I am away, Doppler shift is still going to be the same. Right, so let's check this maximum frequency. The maximum frequency, F max, is 4.5743 times 10 to the 14 hertz. And that corresponds to the stars approaching us. It's coming straight towards us. Because then it's turning. Right? Here down here, the star is coming straight towards us. Right now, it's not going to keep going, right? But it's right now coming towards us. So the light is Doppler shifted according to an approaching source. But I know that that's equal to the frequency at which it is emitted. Let me not write zeros, write emit, divided by 1 minus V of the source divided by c, the speed of light, in vacuum. As I say, maybe we should write it down once. The speed of light is about 3 times 10 to the 8 meters per second. Which is very fast, but not that fast at the scale of the universe. Like light takes a very long time to get to us from distant places. So I know what this one is, right? I know that the emitted, this light corresponds to the hydrogen line that gets emitted at 4.5732. So I'm going to put this, maybe just label this here, 4.5732 times 10 to the 14 hertz. So what does that mean? That means I can solve for the speed of the source. Source being the star. Of course, I could do the similar calculation for the minimum here. Then I put a plus here, plug in the minimum frequency. I should get the same answer. Of course, there's measurement error in everything, right? Every experiment has measurement error. One of the big assumptions I'm making, of course, is that the system as a whole stays fixed in the sky, doesn't move away from us or towards us. Again, that's not realistic. Realistically, if it's far away from us, the whole thing would be moving away from us as well. Well, again, it depends. Within our galaxy, it might be coming towards us. But I'm going to ignore the overall motion. It would shift the whole graph up or down. Right, we're just going to focus on the two stars rotating around each other. We can solve for V source, and what we should find, now of course I did the math beforehand, this is about 72.7 kilometers a second. That is how fast the stars are circling around each other, or rather around their common center. Now what else do I know about this? Well, I have this graph here, so what I see is not only what the frequencies are, but also how long it takes for them to repeat. So what I see is it takes 10 days for one full cycle. Right now it's coming towards us. Now the star's moving away from us. Now the star's coming towards us. Right, and we gain a maximum. So the period is something we can read off the graph. The period t is equal to 10 days, which is 864,000 seconds. Alright, so now I've got the speed, I've got a period, but I know that the speed of the source, the speed of the star, right, is 2 pi r over t. So I can solve for r, because I know t, just from the graph, how long does it take to repeat, and I know the speed of the source. We figured it out from the variation using what we know about Doppler effect. Oh, should we have used the relativistic Doppler effect because it's light? Maybe, but the speed of the source, right, 72 kilometers, again it's fast, but it's tiny compared to the speed of light. So I think we're good doing it like this. So we can solve for r. And if you plow through the math, you should find that the r with those numbers comes to around very close to 10 million kilometers. So that's about 1/15 of the distance between the Earth and our Sun. So they're fairly close to each other. So can I find the mass from that now? That's what my other claim, right? I found the distance between them. It's twice that, 20 million kilometers. The radius of the circle being 10 million kilometers. Can I find the mass? Yes, I can, because I understand gravity, right? I'm going to find the mass using our understanding of gravity, our understanding of gravity and circular motion. Of course, the reason the two suns go in a circle around each other, the two stars go in a circle and don't just keep going in straight lines off into the distance, is because of the gravitational pull. So we're going to have the centripetal force is equal to gravity. Just write gravity. Centripetal force is the mass of those stars times v squared over r, right? We know v and we know r. Those are the stars, the star speed. What's equal to the force of gravity is g times the first mass times the second mass. They're the same, right? Two stars divided by the distance between them squared. We could be a little bit careful here, because the distance between them, between the two stars, is not r, it's 2r, because it's the diameter of the circle. Divided by 2r squared, and I know all the values, right? G is g, it's a constant. V I worked out, I worked out. I can just solve this for the mass. Now you do this, you just rearrange it, you cancel an m, rearrange. You're gonna get m is equal to, if my math isn't mistaken, about 3.17 times 10 to the 30 kilograms. Is that heavy? Well, our sun has a mass, and the mass of our sun is often written like this, m with the subscript dot with a circle. It's about 2 times 10 to the 30. I think 1.99 is closer, times 10 to the 30 kilograms. So the mass of our stars in our binary star system is about 1.6 times the mass of our sun. So a bit heavier, not hugely heavier, but you know, a bit bigger, a bit heavier than our sun. So we figured out the mass of those stars just by looking at, where is it, the data disk, right, the light pattern. And based on what we know about spectral lines, there's a bit of chemistry in there, atomic physics, depending how you look at it, both. Understanding circular motion, understanding the Doppler effect. Now, of course, this was a very simplified example, right? How would we know that the masses of the stars is the same? Well, we'd have multiple patterns to work with. We can use other physics that we know. Maybe, realistically, we would not see that system sort of from down here, like edge on, right? Maybe look at it so from above, like here, and then the stars wouldn't be coming towards us in a straight line ever. Again, there are different ways of dealing with it, right? This was not a realistic calculation, but it was a calculation that displayed the kind of principle, the kind of thinking that goes into analyzing the data that we get watching the light of those stars. And it used the Doppler effect. Another interesting little effect that occurs, just as a little addition to say at the end of all of this, is that let's imagine there's just one star, or it doesn't matter if there are two of them, you just look at one of them right now. Here's the star. Now stars actually, they will also spin, right? A bit like the Earth spins. That means that this side of the star is coming towards us. This side of the star is going away from us. And all the intermediate stages, at the same time. So what does that do if you look at one of those spectral lines, right? The spectral line right now, if this is the wavelength, right, and you ask, where do I see something? And then you say, I'm seeing a bright light at this frequency at 656 nanometers. That's what I expect to see. That is the hydrogen line that I was talking about. Well, actually, what you're going to see is that this sort of gets blurred a bit and looks more sort of like this. You see some frequencies a little bit lower, lower wavelength, a little bit higher wavelength. These lines get blurred. Just by looking at how wide are those lines, how much are they blurred, we can maybe make certain inferences about the speed at which the star rotates, which gives us more insights that we can combine with other physics and so on. So this thing is, hundreds of light years away, maybe more. And we just see this pattern of light, yet there's so much we can infer from it. And one piece of that puzzle is Doppler effect. Thanks for watching.